Okay, so hi everyone. Today I'll be discussing the tree coloring problem that was the part of Hello 2026 Codeforces round. Especially we are discussing both D1 and D2. Um, First, let's try to understand the problem. We are given a rooted tree consisting of n vertices numbered from 1 to n, where the root has index 1 and each vertex is initially wide. Define di as the distance from the root to ith vertex, and we can perform these operations any number of times. We select a subset S of wide vertices such that no two nodes in S are connected by an edge or have the same distance to node 1. Um, okay, I mean, you could just read up this problem statement, and I would be briefly describing what the problem is. So basically, we have a tree, right? Uh, and then initially, all of them are colored white, and we have to color them, right? So in one operation, what we can do is that we could select a subset of nodes. Say I choose this, uh, and then this. All right. The subset should be such that none of these nodes should be connected via an edge, direct edge. Say if I choose this node, particular node, say 1, I can't choose this node 2 or this node 3. Again, all the nodes in subset, any of two nodes in subset should not belong to same level. Say this is level 0, L0. 2 and 3 belongs to level 1. Say this is 4, this is 5, this is 6, this is 7, and this is 8, right? Then 4, 7 and 8 belongs to level 2, and finally uh, 5 and 6 belongs to level 3. So what are our conditions is that no two edges should be connected directly. Second condition is that none of them should belong to same level. I think we have to, right? Yeah, that's all. So we have to perform minimum operations, and what we have to report, say for D1, we just have to report what's the minimum number of operation we can perform so that all the colors, all the nodes in tree are colored. And what we mean by an operation refers choosing a subset and coloring them. I hope we are on same page and now we have understood the problem. uh, by this In the meantime, let's also understand what problem D2 is demanding from us. uh, D2 is demanding to elaborate those operations. In D1 we'll find the minimum number of operations, minimum number of operations, and in D2 we have to elaborate those operations, right? um, what do I mean by elaborate those operations? Say in operation 1 I choose 1, 4 and 6. So I should be reporting that in operation first I have to report similar to D1 the minimum number of operations. After that, in operation 1 I should be reporting that I have chosen 3 nodes. Those were 1, 4 and 6, then and so on. I hope um, we understood the problem statement, the inputs, and I mean the input is simple, and the number of nodes in the tree, and followed by n minus 1 edges, by which we would be creating a tree. So if we are at a point where we have understood the problem statement, input and output, let's just move forward and start understanding or start implementing the strategy by which we'll be solving D1. That is, first we'll find the minimum number of operations that are required, um, so that we could entirely color the tree, right? um, so to D1, what are our observations? So our observations are that, say, we can't color, say this is a level LX, generalized version, and we have k nodes. So we for sure know that we can't color um, any of these nodes together. So a lower bound for our solution would be k, right? I mean, we definitely have to take k turns, and I mean, in one turn I could color this one, then I would pick this, but in uh, none of uh, out of any turn I can't pick more than one basically from this level, right? Because the depth should be equal to, I mean, if I choose uh, for any two nodes di and dj in my subset k, if I choose subset k and choose any two nodes di dj, then depth of I should not be equal to depth of j. It's one of our condition that is given here, right? Y belong to s, x is not equal to y, dx should be not equal to dy. So the lower bound of a solution is k, right? And um, you might be thinking, okay, it's very simple, would be performing an BFS kind of thing, um, and then we just uh, be storing the number of per level, and then we'd be having in, uh, we'll be having an answer or max initialized to 0, and for every level we'll check is max greater than, I mean, if the size of level is greater than maxi, would be updating our maxi to the size of level. But there can be one problem, right? Say if there is a single node and it is connected with every node in this present level, so our answer could be k plus 1, right? I mean, we can't color any of these nodes together at the same time. We actually cannot color the parent at the same time because there is a direct edge, right? So we at least need uh, if there are k nodes here, k plus 1, and the maximum of these would be our answer. So one thing we refer from this that is that um, we'd be seeing every level, the answer or the result is either maximum of size of all level, oh fuck, right here is equal to max of uh, level I, where I equal to 0 to max depth. Also result equal to maximum of 1 plus children of I. For every node, if it's children's plus 1, we're getting the idea, right? So that's pretty much I have done in my solution. Also, this solution is heavily inspired from tourist, so you could also be performing, you can also have something like q of llq, and then you could have, you can simply keep a vector of ll, say level, and then you just perform a plain BFS. That's pretty much it. But yeah, because there are some things we'll use in D2, I just kept the solution as it is or as inspired from tourists. So yeah, so we're just reading the input. After that, It's just plain DFS. Distance represent the distance from node 0 to node I. Then parent vector array parent vector parent represents what's the parent of ith node. Children of I represent number of children in ith node, and that's pretty much it. I mean, yeah, we have the same thing. Yeah, I mean, this loop could look different, but it is as simple as that. I mean, um, you could just, if you don't like this, you could also res equal to max of res comma it plus 1. Yeah, I mean, you still will get the correct answer. So if we have understood D1, now it's time we move to D2, because um, I feel that is much more interesting than D1. So in D2, we are required to color, right? And uh, and while we color, we do have to keep these two things in our mind, so that if x, I mean, for every subset we choose S, x comma y say any arbitrary two nodes, then uh, d of x should not be equal to d of y if uh, x is not equal to y. Also, there should not be any direct edge, right? So the thing is, how do we color, right? So let me define something. Say ban for every node. Ban of node represent the color I can't actually color to that node, right? um, how do we define this? Ban node is simply the color of its parent of node, right? I mean, we definitely can't color the parent of node. uh, and another thing I'm pretty sure is that, say, at a particular level, say Lx, there are k nodes, then we definitely are gonna use, I mean, at max we can use, we are going to use k plus 1 colors, right? Say if there is in level x, as we discussed, if it belongs to a single, it has a single parent node, then every of these k nodes would be colored differently. Again, the parent would be colored differently, so k plus 1, so there would be k plus 1 colors, right? And we do have a ban thing. So for every node, this is, say this is color C, then for every individual nodes here, ban of these nodes would be C, right? As simple as that. And how are you gonna color? We would be keeping a set of numbers, and we would be inserting 0 to k included, so that there are k plus 1 numbers, and then we'd be coloring it accordingly, right? um, However, there is one subtle problem, right? um, Say I have something like this. We have a single node here, a single node here, a single node here, right? Say we just follow that we'll be picking the first color from the node, and then we'll be using that node, that color for this particular node, and then we'll be removing it from the set, right? And how can why set, you may ask? Because we do compare, right? If, I mean, we can have something like this, something similar to this. Would be checking its parent color, I mean, we'll be getting into here very soon, but just let me say, if its parent color is the same color, we'll be just moving the what do we call iterator forward, and then we'll be using that color, right? And as simple as removing it from the set, so it becomes much more simpler. Yeah. So moving our strategy, keeping our strategy behind, say we have this as uh, color 0. I mean, we colored this as 0, and I mean, I would better write here, I colored this as 0 and colored this as 1 2, right? So what will be the problem is that, say we come here and we check, and we have 3 nodes, then I can at max, uh, huh, if I have 3 nodes, right, then I would be at max needing 4 colors, say 0, 1, 2, and 3. um, I come here, I check here, is 0 covered? I say yes. Then I would be picking, I mean, for this node the band would be 0, right? Then I would be picking 1, and I would be coloring 1 and removing it from the set. I say alright, I would be coming to this node. uh, I would be checking, is 0 banned for this node? I would say no. Then I would be using 0 and removing 0 from my set, right? Then moving forward, I have 2. So I would be saying, is 2 banned from this, for this node? I'd be saying, yeah, it's definitely banned for this node. So I'd be moving forward, and I would be coloring this node as 3, right? The problem is that, is this optimal? I mean, when I would be using result, coloring is as similar as, if I say color 0, I mean I'm coming it as in 0th turn. I say 1, I mean I'm coming in first turn, second turn, and this is third turn. So I would be coloring this node as first turn. uh, I'd be coloring this node in my 0th turn, and I'd be coloring this node as my third turn. uh, is this optimal? I mean, no. You could find it as, I mean, I could color this node as 2. This can still remain as 0, and I could be using 1. I mean, I'm coloring these 3 in 3 turns, compared here where I'm using 4 turns. So this is a simple catch. Also, uh, if we somehow store our uh, levels in an left to right manner, I mean, if I fix my tree, and then I store them from left to right. I mean, what do I mean by left to right? I hope you understand. Say this is my tree, I store them in order. I mean, it's not level wise in order, say something like that. I mean, if these this node come first, then its children should become first in the next level to it. I hope you understand for this informal description, but yeah, pretty much it. And then, if there are 2 nodes, I choose the first node, and I choose the last node. So where is the problem? I mean, the problem at most will occur at my last node. So if I use its band color, I mean band color, and I can definitely color, if there are more than one nodes, I can definitely use it in my first node children, or any node children which don't share the same band color, so that I would be end up using its particular band color, and then I could, for this node, I could be using uh, any of other color. I mean, it's as simple as it can be proved using pigeonhole theorem, I believe. I mean, you remove one, then there becomes a space for another. Yeah, that's pretty much it. And how do you uh, do the what is implementation? Yeah. So um, the remaining till here it remains same as D1, but starting from here we have color n. So color n, or I mean, you can just define as a turn n, that doesn't matter. For zeroth node we'd be using 0, and then for every subsequent levels beneath it would be start coloring them. Ban of j um, is as simple as like the parent of the particular node in that level, that is parent of level of I is current level, j is the node in the level I, parent is parent of that, color is the color of parent. There are pretty much it. I mean, you could write something ll node equal to level of I comma j, right? And then ll parent of this node equal to parent of node, and then color, sorry my bad, ll color of parent of this node equal to color of parent of this node. I mean, banj is equal to color. Yeah, I mean, you could do this, but yeah, I mean, there are so much packed in here. I'm really sorry, but I can't help. And then we're just having a set of colors, that is, if there are size length of, I mean, if there are k nodes in particular level, we have k plus 1 colors, and we are just putting the colors. I mean, we are coloring the node, and here is the check statement, and then yeah, pretty much it. And then there are operations. So yeah, what I said earlier, that color represents the turn. So operation for turn I have all those nodes that are colored as color I, and yeah, that's all. um, that's pretty much it, and we do the output thing, and we're good to go. I hope yeah, I mean, you don't see these outputs matching, because I mean, yeah, who cares? But it will definitely get submitted, and I mean, you're definitely getting aces here. um, I hope I was able to translate the information correctly to you. If you feel something was missing, something was off, I was wrong somewhere, do let me know. It would be really helpful. Yeah, that's pretty much it for this video. Thank you.